Welcome to the tutorial PowerXL DA1 frequency inverter optimizing a permanent magnet motor. This tutorial shows how to optimize an exemplary permanent magnet motor on a PowerXL DA1 frequency inverter. The following technical requirements must be met: a DA1 frequency inverter, a serial communication cable DX-CBL-PC3M0 or a Bluetooth communication stick DX-COM-Stick3, and the programming software drivesConnect. This video tutorial is based on the displayed motor datasheet, the set values for the motor parameters, the switching frequencies, the selected control mode, and the motor values determined during the motor identification run. Detailed explanations of the relevant settings are shown in the displayed video PowerXL DA1 frequency inverter commissioning a permanent magnet motor. To check the internal motor model, the drive should be run with load approximately 50% at approximately 50 to 100% rated speed. At the reached speed, the monitor parameter magnetizing current ID P014 should then be checked. The following settings are made for this in the real-time edit mode. The acceleration time P103 is set to 10 seconds. Due to the communication stick still locked, the message appears: "This device supports remote unlocking. Would you like to remotely unlock this device?" This question is confirmed with yes. After unlocking, the deceleration time P104 is also set to 10 seconds. The reference speed is then specified via fixed frequency 1 P201 at 1000 RPM. Switching to the monitor tab takes place, and the boxes visible in the real-time edit mode for updating the parameters P014 ID and P015 IQ are selected. The monitor parameter P014 magnetizing current ID should be around 0 in static mode, while the value of IQ should be around the level of the displayed motor current. If the value of the magnetizing current ID is seriously greater than 0, the value of P107, motor norm voltage, must be corrected and a new identification run must be started for the optimization of the internal motor model. The magnetizing time T excitation V by F, which can be set with P712, causes a delay between the enable and the ramp up of the output frequency when P401 is equal 3 or 4 is selected. This is used to align the rotor and to generate the magnetizing current in the motor windings. The magnetizing current is 50% of the value set with P108 motor norm current. If the value of P712 is too small, this can lead to losses in the control behavior and even to shutdowns at startup. In this application, a value of P712 equal 10 milliseconds can be used. For optimizing motor behavior at startup and low speeds, parameters P714 torque boost and P715 F torque boost limit are useful. In this example, the following values have been found to be optimal: P714 equal 25% and P715 equal 10%. These values are application dependent and should be adjusted. A note: a too high value of P714 torque boost can lead to increased motor current and thus to higher heating of the motor. If the value of P714 is too high, the set maximum torque max motoring of P407 will be reached, which would lead to a reduction of the output frequency, and thus the DA1 would not be able to accelerate to the desired set point frequency. In extreme cases, an overcurrent shutdown may occur. The load inertia factor parameter P710 also allows the ratio of the load and the motor inertias to be taken into account in the internal calculation. The value of P710 is calculated by dividing the total moment of inertia, motor, load, etc., by the moment of inertia of the motor multiplied by 10. If the moments of inertia are not known, it is recommended not to change the factory settings with P710 equal 10. To check the setting, the acceleration and deceleration times are set to 30 seconds and the stop mode, ramp to stop, is selected. For the observation of the complete frequency range, the fixed frequency F-fix1 P201 is also increased to 1500 RPM. Compared to a standard induction motor with the same rated power, the PM motor has a lower mass moment of inertia. Therefore, for more dynamic operation with the internal speed controller, the proportional gain MSC KP P403 can be increased and the integral gain MSC TI P404 can be reduced. Instead of the factory setting of MSC KP 50%, a value of 250% can be used in this application example without any problems, and for MSCTI a value of 0.025 seconds instead of 0.050 seconds. For performance control, the settings of the data logger are adjusted. Instead of trigger on event, continuous run is now selected. For the second channel, the motor speed is to be displayed, and for the third channel, the speed reference. The fourth channel displays the DC bus voltage. A ramp up to nominal speed without load is performed, followed by a stop via ramp. Here a long acceleration time was deliberately chosen to show the effect of the voltage boost at low speeds. After successful recording, the mouse can be moved over the recording, for example with the right line, to view individual operating points in detail. Finally, there is a ramp up with a short ramp time at 100% constant load followed by a long deceleration time. The constant load is specified here by using a 15 kV load machine. For this, the acceleration time is set to 3 seconds in real-time edit mode. The set deceleration time of 30 seconds is kept. Due to the short ramp time, the DA1 enters the overload range with approximately 21 amp, which is indicated with dots in the display. At the reference speed reached and during the subsequent slow deceleration, the DA1 runs with the rated motor current of 14.2 amp. Due to a too small selected scaling with 2 amps per diff, the motor current recorded exceeds the maximum displayable range of 10 diff. Here no recording with new scaling is necessary, but the original value is corrected to 5 amp per diff. As before, individual operating points, for example start or stop phase, can be viewed in detail after recording. Thank you for your attention.